2.6, we're going to be looking at related rates. And when we're looking at 2.6, a lot of what we did in 2.5 is going to build into this, because you're going to see some of those parametrics like we were doing last section of taking the derivative in regards to time in with these variables. And so it is going to be kind of a word problem section, and there's not a lot we're going to say this section, but make sure that you're prepared for this, you're ready for this, and if you haven't been successful in 2.5, let's clear that up and then move to 2.6. So what I want to do is I want to just kind of work an example and talk through this and show you some things, and then we'll look more into kind of some more like responses or defining of it. But again, it's not a long section, it's just going to build on 2.5. So what we're looking at here, as you can see, I already have a cone drawn here. If we were to look at the volume of a cone, the formula for volume of a cone is V equal to pi over 3 r squared h. And that's a volume that you've probably seen before. You probably have to Google it or look it up to get you there. But this is just our regular volume of an of a cone. And so if we think about this, then let's see, we've got our r, which is our radius, and this is the radius of the top of your cone. And then you got h, your height, which this is this distance here, how tall that cone is. And if we begin to look at volume and think of a couple of situations, we could think of this being maybe, think of a childhood memory of a snow cone cup, and you think about filling up that snow cone cup with like shaved ice. So we could talk about how fast are we filling up the snow cone, or we could take that cone and we could say, okay, what if this was like the top of a sand timer, like an hourglass, and we could say, okay, how quickly is the volume changing in that hourglass? Like, for instance, how quickly is the sand filling up, or how quickly is the sand leaving? So like we saw with parametric equations, if we're looking at the volume of this, we then can look at the time aspect and say, okay, how are we filling this up, or how are we emptying this, and what is the rate at which that's going? When we begin to use words like this, like rate, etc., we go, oh, derivative, rate, slope, derivative, all those words are in the same category. So what I want to do is I want to take this volume equation. I want to take my volume equal to pi over 3 r squared h. And I want to take the derivative of this equation with respect to time, like we did with our parametrics in 2.5. Because if I take the derivative with respect to time, this is going to show me how quickly it is emptying, or how quickly it is filling up, or the rate of change of the volume. And so if I take the derivative of that with respect to time, that means my V in terms of the derivative would be dV dt, the derivative of your volume with respect to time. And that means if I'm looking at my r, or my r squared in this problem, thinking about derivatives, that would be 2r, bringing down that exponent, subtracting 1 from it, times the derivative of r with respect to time, thinking about what the derivative of r would be, like your chain rule. And if you look at your h, its derivative would be 1, because the derivative of a constant just is that coefficient, but this is the derivative of h with respect to time. And I'm making these small fractions or notations because in our basic problems, we took the derivative of y with respect to x. That gave us the dy dx. But then we were just working with the letter x's. So if I'm taking it with respect to time, only if I had a t in there would I not have to put a fraction. So now if I take the derivative of both sides of this function here with respect to time, this would be equal to dv dt, so the derivative of v with respect to t. Pi over 3 is just a constant or a coefficient, so it's going to stay out front. And then we're going to work with this piece here, r squared h. So we're going to have to apply our product rule. The derivative of the first, which we already said that was 2r dr dt, times the second, which is h, plus the first, r squared, times the derivative of the second, which was dh dt. And then if I clean this up a little bit, this gives me dv dt is equal to, I'm going to leave that pi over 3 out front. So this would be 2rh dr dt, I'm just reordering those letters, plus r squared dh dt. And so this is, let's just kind of make this notation. This is the rate of change of volume with respect to time. And so I know this got complicated real quick, and we're going to see more discussion of the ins and outs as we move into our next section as well. But there comes a basis for why we need to do this. So now at this point we could say, okay, if we know the radius and we know the height and we know how quickly the height is changing or how quickly the radius is changing, we can tell you how quickly or slowly the volume is changing. So we're taking all the rules we've done thus far and we're adding them to this new concept of doing it with related to time, again, like we saw with our parametrics. So let's do another example. And let's look at this. It says two rates that are related. So suppose we have x and y and they are differentiable functions of t with y equal to x squared plus 3. We want to find dy dt when x is 1 and find dx dt, which is equal to 2. And so what I'm going to do is I'm going to take this equation here, y equal to x squared plus 3. And I'm going to take the derivative of that with respect to t. So let's kind of go slowly through this and see what we can do. The derivative of y would be 1 with respect to t would be dy dt equal to the derivative of x squared would be 2x. So you do all your basic rules you know. But since it's with respect to t, we're going to have to put a dx dt there. Plus the derivative of 3, which is 0. Now I'm going to go ahead and clean that up a little bit. So that gives me just dy dt equal to 2x dx dt. Now it gave us more information. It says x is 1 and dx dt is 2. So I'm going to plug in that information. So I'm saying, okay, well, dy dt is going to stay the same. Equal to 2. We know x to be 1 and we know dx dt to be 2. So finishing that up, multiplying that all together gives me a 4. So that says that my y is changing at a rate of 4 because we had more information with this one. One more example, and then I'm going to let you go on your own so you can try some examples and work with it, but contact me if you need any assistance. Find the rate of change of the ripples given r is equal to 4 and dr dt is equal to 1 feet per second. So let me tell you more information. This is like ripples in a pond. Say you take a rock and you try to skid it across the pond, or you just took a rock and you just threw it in. The ripples that it creates, you can see they start real small, and then they get bigger, and then they get bigger, and the ripples just start going out from there in this kind of concentric motion. And so if I look at the shape that these ripples are making, this is creating a shape such as an area of pi r squared, just maybe doing the area of each circle. So with this one, they didn't tell me, hey, area is equal to pi r squared, like we saw in the previous one with the equation. We just have to know what we're working with. Well, we're working with circles, and here's a formula I know about circles. That's a pretty basic formula. We all kind of know pi r squared. And so what I want to do is I want to take the derivative of this function with respect to time and see at what rate the ripples are moving outward. And so if I do this with respect to time, that would give me dA dt equal to pi is just going to go along for the ride The derivative of r squared is 2r, and then I need a dr dt, the derivative of r with respect to t. So cleaning that up and just really putting it in a better order, that would be 2 pi r dr dt. And then they gave me additional information. What is it when r is 4? And the rate of change of your radius is 1 feet per second. So I'm going to plug all that in. So that would be dA dt is equal to 2 pi. I know r to be 4 and dr dt to be 1. So I'm going to multiply that all together, and that gives me 8 pi, that's an exact number, feet per second. Now I like exact numbers, so I would just leave it as 8 pi. Now if the instructions tell you, or underneath the answer blank tells you round to 3 decimal places, okay, go grab your scientific calculator and use your pi button. But if it does not, just leave it as exact answers such as 8 pi. Exact answer, I didn't have to round it, and I get my answer. So what you're going to see in this section is applying time to multiple situations. The homework is not going to be lengthy because they are time consuming, but please reach out if you need assistance.